So welcome back, everyone. Today we'll be discussing the basics of quantum algorithm. In particular, we'll be discussing what bits are and what qubits are, or quantum bits. We will also be discussing how to implement functions in a quantum computer by using unitary operation and unitary gates. And finally, we'll be discussing some of the features that give quantum computer an advantage. In particular, we will be introducing the concept of quantum parallelism. Now, a bit is a binary object that can take the value of 0 or 1. This has to be contrasted with a quantum bit, or a qubit in short, which is actually a quantum object that can take the state vector value of 0 or 1. Not just this, actually, it can also take any value in between them. This concept can be very well visualized by considering a pure state on a Bloch sphere, that is a sphere of radius 1, where at the surface of which one can find any state vector psi as a linear combination of anything of state vector 0 and state vector 1 with arbitrary coefficient normalized to 1. Of course, in quantum computers as well as in classical computers, we don't just use a single bit. We in fact require usually a lot of them, and in particular we can compress them into n-bit strings that can be described as decimal number by considering the following rule. When we have a list of n binary number, so this string that we can see on the screen over here, that contains a lot of zeros and 1, this can actually be seen as a decimal number just by multiplying each of this bit with the appropriate power of 2 and summing them up. Likewise, n-qubit state can be described as a tensor product between qubit states. So in particular, we can consider n-qubit state. And throughout this course, we will be using the shorthand notation where we actually neglect to write the tensor product, and we just compress everything into a single string. Sometimes we will also use the notation where the string will be just represented as a decimal number just by using the capital X, this capital X notation in the vector space here, in the vector state here. Now, quantum computation. The main ingredients of quantum computation start by considering an initialization procedure, where essentially you have to prepare a suitable qubit state. Then we go to the operation, and the operation in quantum computer, and this is very important, are only given by unitary, or in other words, reversible gates. This operation can be quite complex, but at the end of the day, we have to measure the state and get back a classical list of bit. And in this step, which is the measurement step, the qubit state collapses to either 0 or 1. So each of the qubit after measurement will be given a value of 0 or 1. Now, the main quantum principles behind the quantum computer are the principle of superposition and entanglement. Now, by superposition, we mean what I essentially meant before, that a qubit state does not only take the value of 0 or 1, but can take anything in between. Entanglement is a property of multiple qubits. In particular, when we have two qubits together, we can let them interact, and the interaction will kind of prepare some states, and if the states is particularly is prepared in a particular way, then there are correlations that will be pertained even if the qubit state will be spread apart and very far away from each other. Now, to see why this can lead to a very nice advantage in quantum computers, one can also take the very simple and very naive example of trying to run out of a maze. In a classical computer, the classical computer will try all the possibilities. On the other hand, a quantum computer can try all the possibilities in a same go, and this is essentially the concept of quantum parallelism. Functions are operations that take as an input an n-bit string and outputs a single bit with value 0 or 1. Now, in quantum computer, typically we work with circuits that are these little blocks that you can see over here. We can see that if this was a quantum computer, it would take an n-bit string, or that we call capital X as before, and outputs a function of this n-bit string that is a single bit 0 or 1. Now, as I mentioned before, quantum operation needs to be reversible. And this obviously is an irreversible operation because you take an n-bit string input and it outputs only 1 bit. So you lose all the information about the input. And for this reason, this is not compatible with quantum gates. To make it compatible with quantum gates, we need to implement this function as unitary gates. And the unitary gates needs to preserve information from the input. There's a simple fix for this, and in particular, it's to have a unitary function that takes the input registry X and processes it as it is, and only acts on an ancillary qubit with state Y, and it acts as an XOR where Y is summed up modulo 2 with a function of the input registry. Now, this is a valid quantum operation, and it's a reversible operation that is compatible, therefore, with quantum gates. Sometimes this unitary function in the middle is called an oracle, and we will see a lot of them throughout this course. Another important concept that we hinted before is the quantum parallelism. Let us try to formulate a little bit better. And in particular, let us consider the following operation. This is called an Hadamard gate. This gate takes an input state, for example, as an input state 0, and when applied to this state, essentially builds up a superposition of 0 and 1 with a positive sign. We will call this state the state plus. Conversely, if we take as an input of this Hadamard gate the state 1, the Hadamard gate will output still a combination between 0 and 1, but with a minus sign. And this we will call the state minus. So let us now combine these two concepts in the following circuit. We now apply first an Hadamard gate to a registry qubit, a qubit in the state 0, and we see that after the Hadamard, it will become the state plus, so the superposition of 0 and 1. After this step, the ancillary qubit in state 0 will be passed as it is, and therefore will remain in the state 0. Let us now apply the oracle U of f, and let's see what happens in this case. What we do see is that the output state is a superposition of the registry in state 0 and the registry in state 1. What happens is very interesting. What happens to the ancillary qubit is very interesting because in this case, the ancillary qubit will evaluate the function when it's 0 or the function when it's 1. And in particular, the final state will be the superposition of these two functions. In other words, this circuit evaluates simultaneously f for 0 and 1. In the next lectures, we will see how to use this property to make quantum computations.